Hello, guys. You're welcome back to this lecture. We are going to continue with discrete probability distributions. This time we'll end with the Poisson distribution. We've looked at the binomial distribution already. So the Poisson distribution is a discrete probability distribution that is useful when events happen at random. Okay. Of course, that is also similar to the binomial. So events happen at random, and the events are independent of each other, just like in the binomial distribution. And when they occur over a period of time or space. Okay, so this, if you like, is the difference between the Poisson and the binomial. So in the Poisson distribution, these events are going to occur over some space or by time period, okay? For example, when a density of items is distributed over a given area or volume, okay? For example, the number of plants that are growing per acre, or the number of defects in a given length of videotape, or if you like, the number of typographical errors, typos that you can find in a distributed in a book. Okay, so you take social studies or whatever for junior high, and you have all these typographical errors distributed over it. How do you compute the mean and then the stuff? All right, okay. So that is, so in those circumstances, you use the Poisson distribution. The main parameter, actually the only parameter that you need for the Poisson distribution is the mean. Okay, the mean number of events occurring within the time or within the space. If you get the mean, then it's easier to compute the probabilities. Okay, so it's quite useful. So here's the formula for the Poisson distribution. The probability of X occurrences in an interval of time or space for a variable where lambda is the mean number of occurrences per unit time or space is given by this formula. Okay, so once I have the mean, the probability of X occurrences, where X could be 0, 1, 2, and so on. Okay, X cannot be negative, so start from 0, whole numbers is positive. So once I know the mean occurrence within a time period or within some space, then I can compute the probability of, let's say, 0 occurrences or 1 occurrence or 2 or 3, and use this formula here. E is this number here, which is approximately equal to 2.73. So I can just use this and compute it. So here are some examples. If suppose that for an event the mean is 1, okay, then you can compute for different values of X's, right? And that will give you this distribution. Cool. Okay, so this should actually be dotted lines. I use a continuous thing to plot it, but they are really discrete. Okay, for 0, for 1, for 2, for 3, you get an idea. And then if your mean was, for example, 2, then the distribution becomes this black curve here. If it's 3, it becomes this. Okay. See how the hump is sort of moving to the right, okay, as lambda increases. Okay, so that's the Poisson distribution. This is the formula that you need to know to be able to compute the probability for Poisson distribution. So look at just 2 or so examples, or 1. So let's look at this. If there are 200 typographical errors randomly distributed in the 500-page manuscript, okay, find the probability that a given page contains A, exactly 1 error, and then B, exactly 3 errors. Okay, so you have a 200-page manuscript that is going to be published as a book or something, and you want to compute the number of the probability of an error on a page. So there are 200 errors that are distributed over 500 pages. So the mean number of errors per page, of course, would be 200 divided by 500. 2 or 5, that is 0.4. So we know the mean. So once we know the mean, can apply the Poisson distribution, probability that X is exactly 1, given that the mean is 0.4, is given by this. So you have e to the negative lambda, lambda to the 1, all over 1 factorial, calculate that, we have 0.26881. Okay, which means that there is a 27% chance, right? This is 26.8. That's about 27% chance that any given page will contain one error. Okay, so the chance that if I flip a page, I'm going to find one error is 27%. What of 3 errors? If you compute it using the same formula, you get 0.0072. Okay, so this is less than 1%. So the probability that a given page will contain 3 errors is less than 1%. Okay, it's like 0.7%. Okay, so that's what that means. Okay, good. So let's look at our second example. A pharmacy store receives, on the average, 3 phone calls per hour. Okay, on its toll-free number. This is number. Okay, typographical error. All right. So on average, so when you see on average, then you should be thinking of Poisson, right? Because you need the average to be able to compute the Poisson probabilities. Okay. So the pharmacy store receives on average 3 phone calls per hour on its toll-free number. So the average, the lambda, if you like, is 3. For any given hour, you want to find the probability that it will receive the following. To receive at most 3 calls, at least 3 calls, okay? And then to receive 5 or more calls. Okay, how do you compute those? All right, so the first thing is that we recognize one, 2, or 3 calls, right? That's at most 3 calls. So you compute the probability for each of this and we add them up, okay? Using the, the additive law of probabilities. So probability of 0 calls plus probability of 1 plus probability of 3 plus probability of, 2, and then probability of 3. Okay, so plug them into the formula. Remember the 0 factorial is 1, okay? And then you compute this, calculate all of that, and then you use 0.6472. Okay, so there is a about 65% chance that they will receive at most 3 calls, okay, for a given hour. That is what this means. And then B, at least 3 calls. What does it mean to at least 3? Okay. This was at most. Okay. At least 3 means 3 and more. 3, 4, 5, 6, 7. Okay. Up to infinity, if you like. But you can't compute that. So you have to use the principle of, the complement. Find the probability of, less than 3, right? 0, 1, and 2, and subtract the answer from 1. That is what is going to help you to compute that. Okay, so at least 3 calls means 3 or more calls. So it is easier to find a probability of 0, 1, and 2 calls, and then you subtract your answer from 1 to get the required probability. Okay, so you compute the probability of 0, 1, and 2. If you sum them, you're going to get 0.4232. Subtract that answer from 1, and that gives you 0.5768. All right, because you can't calculate 3, 4, 5, 6, 7, 8, 9, 10, and so on. Okay, it's impossible to do that. So this is the approach to use. It's similar to the last one. You want to find the probability that they have 5 or more calls. So again, this is like 5, 6, 7, 8, and so on. You can't compute that. So the way to get that is to compute from 0 to 4. right? Probability of 0 or 1 or 2 or 3 or 4. And then you subtract your answer from 1, all right, to get this. Okay, so that's what is done here. Probability of 0, of 1, of 2, of 3, of 4. Sum them, you have 0.8152. Subtract it from 1, then you have 0.1848. All right. Okay, so that's how you apply the Poisson formula. Okay, so from these events, the most likely that is to occur is the one in part A. Okay, part A has probability of about 65%. This one is about 58%. This is about 18%. So the first one is the most likely to occur, having three calls, right? At most 3 calls. And then the least to occur is this one, right? The part C, because only 18%. Okay, good. So here are some exercises that you can try on someone to test your knowledge of the Poisson distribution. Great. Okay, so that brings us to the end of discrete probability distributions. All right, I'll come your way again maybe later.